the atomic table in a style somewhat similar to Mendeleev, based on your solutions to atomic physics. Now, it works out that for sodium, for example, there are two, well, debatable, inner shells of electrons. The innermost shell, the S, there are 2 electrons, and then the next shell, like 8, well, 2 and 6, they're the so-called P electrons. Well, there's, well, I don't know too much about the details, but anyway, so two electrons like in the inner shell, and then let's say 8. That's a bit more detailed than that. So that's in a sense a complete shell, and 1 extra, so that's the 11th electron, and it's sort of on its own in an outer layer, so to speak, and able to bond, for example, with chlorine, which has 7 electrons in its outer layer, and would like one more to make 8. 8 seems to make the atoms more stable. And to understand that kind of thing, you'd need to go into quantum chemistry, which is a fascinating topic in its own right. Anyway, so the sodium atom behaves a bit like a hydrogen atom, because the hydrogen atom also just has 1 electron in its outer layer. Well, inner layer, outer layer, there's only 1 layer, so it's the same thing for hydrogen. But the mathematics and the modelling is somewhat similar for sodium as it is for hydrogen, because just 1 valence, 1 outer layer electron, and the other 10 are in so-called complete layers closer in. Now, because of that, the modelling of the potential energy, the V, is not entirely Coulomb, because the positive charge of the protons in the nucleus, they're sort of screened or masked, modified in a sense, due to the 10 electrons in the closed shells closer into the nucleus. So you don't get the Coulomb energy, what's the word, degeneracy that we're talking a couple of sessions back. But the mathematics is well, that's what the text says. I mean, this is just a sort of verbal description saying, here's another possible example if you're interested, is analysing the spectra of sodium vapour. Like you may know, maybe high school chemistry or something, if you burn sodium, it will give off a very bright yellow light, and there are two bands, if you look at the sodium spectrum, light spectrum, there are 2 very strong yellow, yellow colour, yellow frequency bands of light, and they're called D lines. That's from atomic physics, like S, P, D. Those different letters correspond to different, how can I put it, polar diagrams, I suppose, of the electrons around the nucleus. Like S is spherical, P I suppose means polar, a big guess. D, not quite sure, maybe dipolar. And then I think there's F and G, and, well, there are others. Okay? So, due to the masking of these inner closed shells, the V, the potential that the 11th electron in the outer layer that it feels is not Coulomb, it's more complicated than that due to this screening or masking effect of the inner electrons. But you can go through a similar analysis of spin coupling and so forth as you did for the hydrogen atom. You can solve it for sodium. Alright, now sort of new topic somewhat. In fact, this and the next 3 or 4 sessions will be on the so-called Zeeman effect. And basically, just throw it at you. Basically, the idea is, if you put your atom in a magnetic field, then the very presence of that magnetic field will create new interactions on the electrons in the atom, which generate new interaction terms, new potential energies. So you add potential energy terms to the Hamiltonian, the energy operator, and hence these extra terms in the Hamiltonian will change the eigenfunctions and change the eigenvalues, right? Because the Hamiltonian has changed a little bit. You're perturbing it, meaning changing it by a small amount, by adding these smaller, finer terms to your Hamiltonian. Now, next chapter, chapter 10, is on. It's the theory of perturbation theory. So to perturb is to make a minor change, a minor disturbance to what was going on before. Like you add an extra term to the Hamiltonian. Right? So that the whole chapter is on the theory of perturbation theory, as it's called. So what we're doing now is we're switching on a magnetic field, field strength B, so it's now non-zero, and we'll get a perturbation due to the presence of that magnetic field. And so the next 3-4 sessions are about the Zeeman effect. And what is that effect? And now, perhaps I should, well, before getting into the effect, say a little bit about the language. The Americans, British somewhat less so because they're more European. The Americans tend to pronounce this simply Zeeman. And that's because now the name is actually Dutch from Holland, and ZEE in Dutch language is pronounced zee, like the A sound as in ABC, zee. And zee in Dutch means the sea, like the ocean. So zeeman literally is seaman, in other words sailor. Okay? So, but because Dutch is not it's not a major language, the Americans tend not to know how to pronounce Dutch. I'm only saying it because I lived in Brussels, capital of Europe, for well over a decade, about 15 years I think. And so I speak Dutch because Brussels is bilingual, Dutch and French. So Zeeman, well, the name is certainly Dutch. I'm not sure if he himself was Dutch or German. Dutch is sort of a dialect of Deutsch. So way back, I guess the Dutch were a tribe of Germans in some ways. I don't know enough about the ancient history of the Dutch. Anyway, so effectively the Zeeman, I'll pronounce it in the Dutch way, the Zeeman effect is you get a splitting in the allowed spectral lines when you put the atom in a magnetic field. So you can have a weak magnetic field, strong magnetic field, and the stronger your magnetic field, the greater the splitting, the energy, the allowed energies in your spectrum change. They get modified, they get perturbed due to the Zeeman effect, or Zeeman effect. Right? So just think of this as splitting of the spectral lines due to the presence of a magnetic field. Right? That's the essence of what the Zeeman effect is. Okay, so we switch on a magnetic field, and that means the Hamiltonian will change. We'll get an interaction term, an extra potential energy due to the presence of this magnetic field. And now we won't actually do it because we don't know how to do it yet. We haven't done chapter 10. These next few sessions are a bit of a catch-22. Now, if you're not a native English speaker, what does that mean? A catch-22. Well, it's probably easy to give you an example than try to explain it in the abstract. You see an ad, and the ad wants experienced waiters for their restaurant, and but you don't have any experience. So how can you start to be a waiter? You have to be a waiter to get experience, but you can't get experience because you're not a waiter, because you haven't had experience in the past. So it's a kind of catch-22, or I suppose you could say it's a bit of a chicken-egg argument as well. Like, you know, which comes first? So to understand the Zeeman effect, we need to understand perturbation theory, which is next chapter. But if we don't have the results of perturbation theory, then we can't explain the Zeeman effect, which is now. So, you know, we need both. So it's sequential. We have to do one first. So the textbook does the Zeeman effect first. And so to understand this fully, you'll need to come back from when you have studied chapter 10 and come back to here to understand the theory that we'll be using for the Zeeman effect. Okay? So the next session or so, what we'll be doing is we'll be adding an extra term, potential energy, to the Hamiltonian, and then we will find the perturbation in the allowed eigenvalues of the allowed energy for the energy operator, usually called the Hamiltonian. Right? So that will be next session.